Everybody, video notes 8.1. So we're going to look at reaction rates. Here are the book connections. Please read those sections. So kinetics is the study of how fast chemical reactions occur. You may see fast reactions, you may see slower reactions, but all of these are chemical reactions because new things are forming. So here's a chemical reaction. It looks like it's a combination or synthesis reaction because two elements make a compound. So are iron and oxygen ever going to form iron oxide without colliding? No. So how did this happen? Well, did it happen fast or slow? Well, those are the kinds of questions we can ask. But look, here's some oxygen gas, and the only way it's going to react with iron, here's solid iron, is by hitting the surface of the iron, right? And it has to hit at a certain angle with a certain amount of energy in order for it to happen, because electrons have to be transferred, and you got to make this solid iron oxide. So this is a combination synthesis reaction. And is it fast or slow? Well, it looks like that's been sitting out in the air for a long time, so it might be slow. Okay. So how do we talk about how fast the reactions or how slow? We would talk about the rate. And the rate is always measured in an amount. And in this case, the amount is molarity over time. And so how much reactant disappears over time, or how much product forms over time. So how does rate compare to time? Is if it's a high rate, then it takes, it's a quick, less time, all right? So, like 1 minute, that's a high rate compared to 5 minutes is a low rate, okay? So something is a low rate, then it takes a lot of time. Okay, think about running to class, right? Your rate of getting to class, you got to cover a certain distance in 6 minutes, right? So if you get there in 1 minute, that was a fast rate. If you get there in 6 minutes, they get there faster, so you're not tardy. Okay. So one thing that chemists think about when they think about chemical reactions is collision theory. In order for a chemical reaction to be successful, that's like the home run we talked about in the practice. Molecules must collide. That's the first thing. They'll never react unless they come in contact with each other. And when they hit, they have to have enough energy. Okay. And when they hit, they have to hit at the correct orientation. So that's what we think collision theory is. It's simple but beautiful. Okay. So what does orientation of collisions mean? So in this reaction, we want this chemical, BRNO gas, okay, so here's one of those, to turn into Br2 and 2NO gas molecules, right? So here's one way that if they hit like this, they're coming in, hitting each other, then they can break off into 2 NOs and 1 Br2. All right, that worked. What if they hit this way? Well, then the Br2s can connect to make a bond, and the NOs can break off. What if they hit this way? No reaction. Why? Because it didn't have the right orientation. This is a good, this is good, this is no good. Right? Because it's not the right orientation. So there's lots of different ways, though, that they could orient to make the correct products. Reactions occur in steps, though, like baking a cake. So you want to bake a cake, you got to pour in mix. Right? And then to add other ingredients. Then you got to mix it, stir. Right? Then you got to pour in pan. And then you got to put in the oven to bake. Right? So those are all the steps it takes to get from raw to baked cake. Okay? A lot of steps, right? So the rate determining step is the slowest step, and that controls the rest of the rate of the reaction. So you can do that in 1 second, 2 minutes, 3 minutes. Let's see, pour in the pan, that takes 30 seconds, but then you got to cook it for 40 minutes. So no matter how fast you do these, your cake's not going to get done until after the long step gets done. Okay, so a catalyst makes the reaction speed up, so a catalyst is probably going to affect the slowest step. So rate determining step is the slowest step. So In this cake mixing, it's probably step 5, and that's baking it, right? Okay, it's step 5. Okay. Okay, so, oh, look, now it's a reaction instead of baking a cake. Each step in a reaction is called an elementary step, okay? So if A turns into F in one step, then it's an elementary reaction. If A plus B turns into C in one step, then there's your elementary step. But if A plus B plus E turns into G, and it has to go through these 3 steps, then these are called elementary steps, but there's 3 of them. Okay, so what do you do to see the overall reaction? Whoops, I totally missed that, right? I'm going to try that again. We're going to add them up, all right? Just like these are equal signs in math, all right? We have A plus D plus C plus E plus F plus B. Whoa, that's a lot. Gives us C plus F plus G plus D. Now let's see what we have on both sides. Well, A is only on this side. D is there. I'm going to circle it because it's important. It's on both. C gets formed in the first step, but then gets used up in the second step. So that one's right there. E is only on this side. F gets formed in the second step, but used in the third step. Okay. B is only there once. Now the reason I circled D is because if you notice, D goes in and comes out at the end. Okay, so D is what we call a catalyst. So the reason it's going in the first step is to make that step faster, and the reason it comes out is the catalyst doesn't get used up. Okay, what do we have left then? A plus E plus B, which is what we needed, gives us G with these 3 elementary steps. Okay, what do we call the things that got canceled? C and F, or what we call our intermediates. Intermediates. So they're things that form in one step, form in a step, but get used later. Used later. Okay. Catalyst goes in early, so it's a reactant, well, it's on the reactant side early, but comes out at the end. So a catalyst is something that speeds up a reaction but doesn't get used up. Okay, so these are called elementary steps. You add them all together to get your overall reaction. This is our overall reaction. All right. So, what influences how fast a reaction can go? Well, these things do. Mechanism, nature of reactants, concentration, surface area, temperature, and catalyst. And there's another thing called an inhibitor. Okay? But out of all of these, we have to see, well, how are they going to influence the rate of a reaction? And it has to do with collisions. Okay? What influences the collisions? Okay, the mechanism. Each step in a mechanism takes time, but the slowest step determines the rate. So how is mechanism used to influence rate? The slowest step determines the rate. Nature of reactants. How does that influence the rate? Well, if you have a super complex molecule, whoa, right? It's going to be harder to react to that molecule, right? And then if you have simple reactants, right, they can go slower. If you have solids, liquids, or gases, they can influence the rate because the nature of the reactants. Gases actually react the fastest because they can hit more often. There's more space in between them. They can hit stuff more often. Okay. Factors that we can control that can change the rate of reaction, temperature. Okay, so we can control how hot we put the reactants at, or how cold we put them at. Okay, so why? So higher temperature means more kinetic energy, and so then that's going to make more collisions with more energy. So that's going to make a faster rate. And then vice versa, right? Okay, the opposite for slower. Okay, so temperature. Remember, we have to think about collisions. Concentration. Higher concentration means more particles. What does more particles mean? More particles means more collisions. What does more collisions mean? More effective collisions. If you have more collisions, you're going to have more effective collisions. So that's going to be higher rate. Okay, surface area. Surface area. More surface area means more collisions. Why? So that means faster rate. Well, let's look. All right, so you have your cube. Oh, look at that. I can draw in 3D. Okay, so say that's 1 gram. Or you have a powder. Say that's 1 gram. So remember, collisions have to occur. In this one, only the surfaces are exposed to be able to be hit, right? In this one, you can get hit from all angles, more effective collisions in more surface areas. Okay, effective collisions. So look at that particle can hit on that side, that side, that side. This particle, that side, that side, that side. Okay. Most of the particles are buried inside the cube. Catalyst or an inhibitor. It lowers the activation energy. Okay. So we don't need as much energy to climb the hill, which we'll talk about in a little bit. So then it's a faster rate. Okay. So why do reactions happen in the first place? Well, we have to talk about energy and stability. So energy is conserved in a chemical reaction. And a lot of times the reason a reaction is happening is because products are more stable. Products are more stable. So stability drives reactants when energy is lower. Okay. So if something releases a lot of energy quickly, then that's probably going to be a faster reaction. And if the products are more stable, that's going to be a faster reaction. Okay, so we talked a little bit about bond energies. So if you want to break this bond, you have to add in 413 kilojoules of energy for every mole of that bond to break it. Add that much to break it, okay? And so, this double bond, you have to add 799 kilojoules of energy to break those atoms apart from each other. So anytime you have to start a reaction, you have to break bonds. So we can figure out delta H for a reaction by doing this. All right, we did this in the practice. But every time you have reactants, they have to collide with the right amount of energy, and that right amount of energy is the energy to break the bonds, or to get the bonds starting to break, okay? We also call that activation energy. So every reaction is going to go up first to break bonds. Then you'll get to this activated complex, and then new bonds can form, and that always releases energy, so it's already downhill. So this overall reaction, and this overall reaction, you add in the bonds breaking, bonds break, okay, plus the energy release when bonds form. Okay. So you'll have a positive and a negative number, but you add all that together. You add that together for the delta H. Okay. So based solely on energy, which reaction is more likely to happen? Well, here's your reactants with certain amount of energy. Here's your products. The products are more stable because they're lower in energy, and overall energy is released. So this is more likely to happen because these are more stable, because it's lower than what the reactants were. Okay. So we practice this in class. We'll just do a total here. So in this reaction, there's 2 of these bonds that have to break. And there's 1 of this bond where it's a double bond. And you're going to make 2 of these molecules. So then we have to get our totals. Right? So we have 436 for this, times 2. And then we have the oxygen, which is 499. Okay. And then over here, we have 1, 2, 3, 4 OH bonds. So OH, so 4 times 463. If we do all that, then we find out that this is bonds breaking, so this is positive, and we get a positive 1371. This is bonds forming, All right, so all this is energy released. So 4 times 463 is 1851, 2, and this is negative because it's released, because bonds are forming, and this is absorbed. Okay, so then the total is, you add those together, and you find out, so we got to add all this up, and we find out that we have 481, negative 481 kilojoules, when you add that together. So bonds break, bonds form. The total of that is 481 kilojoules, but it's a negative number because the releases more than the breaking of the bonds. Okay, so this is the exothermic reaction because this is a negative number, and that's the energy release. Okay, how can we translate that into a diagram? Well, now the part about this that you wouldn't know, or I wouldn't know even, is what is the starting energy of the reactants anyway. So we'll just put this at 200, 300 kilojoules. Okay. All right. So we said that 1371 is how much energy it takes to go up. So then we're at 1671. Okay. That's the top of the hill. So that's how much energy it takes to break the bonds. And then we come downhill. Oh man, I forgot 400. Let's make this 800. And then 8 and 13 is 21. 2171. Okay. So then we got to come down to 481 below here. So that would be like 319. All right. I know it's a rough sketch, right? Here's the reactants. Here's the products. The climb up the hill was a total of 1371, which we calculated for the energy to break the bonds. Okay. Then they release 1852 when they form two water molecules, but then the delta H of the overall reaction, this is the delta H, is a total of 481 kilojoules. Okay. And it's negative because the products are lower, they're more stable. Okay. I want you to try this one. Go ahead and give it a go. Right. And then see if you can get negative 2054. Okay, the thing about it is that you have to know what this looks like, so I'll draw this one for you. There's 3 carbons. And then their H, oh, it's an organic molecule. It's called propane. That's what it is, propane. Right. 5 O2s, so we got 5 of those. CO2 looks like this. This is why we did those dot structures, if you remember last semester. And then 4 of those. So remember to multiply that by 5. There's 3 of those, and then there's 4 of those. Okay, so try it and see if you get this. That's what I got, but I could be wrong, so I want you to try and check. Okay, so then once you do that, you would draw an energy diagram for it. Okay, so energy diagrams in general, potential energy diagrams, an exothermic goes low, okay, ends up lower than it started. That's exothermic. Just the endo. Anyway, exo go low. Endo end up higher. Okay. The reactants are always on the left, products on the right. All right. Activation energy is the climb. So you can put dashes if you want, but it's how much energy does it take to get up the hill? How much energy does it take to break the bonds? So a way to write that is E sub A, activation energy. Okay. And look at this one. This has a bigger climb. Right, E sub A. Right, it's to the top of the hill. So what do we call this thing at the top of the hill? It's called a transition state. Transition state. It's on both hills, both tops. Also called the activated complex. Activated complex. All right, so there we go. Oh, wait, there's one more thing. Delta H. So delta H is the heat of the reaction. And this is negative delta H because it's exothermic. And this is heat released. So into the environment, that's what you would see. This is a positive delta H, okay, and that's heat absorbed. overall. Okay, so you always absorb to break bonds and release when bonds form, but overall you don't even need to see the hill to tell if it's endo or exothermic. Okay, so here's a way to remember if you want. Ew, the dog is barfing. Why? Because breaking bonds absorbs energy, so you always go uphill to break. Right? Energy is released when bonds form. There's your RF. So you always go downhill when bonds form. Okay, up to break, down to make. All right. So if it goes up higher than it comes down, then it's going to be endothermic. If it goes up higher than it comes down, that's endo. But if it comes down further than it went up, that's exo. That's endo. Okay. So you got to barf when you make chemical reactions, and then endo ends up, exo goes low. So make sure you can find all of these things on an energy diagram and either calculate them or point them out or give a number for them by reading the diagram. And make sure if you're given that stuff, you can draw one of your own. Here's the general stuff one more time. All right, what does a catalyst do? Okay, so here's our original reaction. This is at about 12 kilojoules, right? 12 kilojoules. And this is at 5. So reactants, products, reactants, products. The delta H is about 7 here and about 7 there. So all of that's the same. Okay, delta H equals -7 kilojoules. All right, so what's the difference? Well, this one, the activation energy goes from 12 to 24. All right, so that's about 12 kilojoules for activation energy. This one only goes up to 20, so 12 to 20. So this is 8 kilojoules for the activation energy. So this is a catalyzed reaction of the same thing. So sometimes when we do a catalyst, all we do is we show with a dashed line. It doesn't change anything but the hill, because then a catalyst gives a reaction a new way to form so that it doesn't have to get to a top of a high hill. Okay, so a catalyst speeds up a reaction. Catalyst speeds up a reaction. Speeds up. Whoa, reaction. But doesn't get used up, and it lowers the activation energy. Okay, so what is kinetics? It's looking at the rate of a chemical reaction. Reactions occur in steps. The slowest step determines the rate. Intermediates are formed and then used up. Catalysts go in at the start somewhere, and then they're there when you're finished, so they come out at the end. Collision theory makes sure that you know that molecules have to collide at with the right energy at the correct angle. And then energy diagrams always up, then down. You got to break them, then make them. Break them, make them. Break them, make them. Okay. And then the top of the hill is the activated complex. Reactants, products. Whoa, that's a lot of stuff. Okay. We'll talk about rate more in the next one, like how to calculate it, but it's amount over time. If the rate goes up, it takes less time. Don't forget that a home run is collision theory, is how we decide collision theory. Reactions occur in steps, break them, make them. Wow, it's a lot of repeating. So anyway, hopefully you learned a lot. Peace out. You're going to see some more slides as you go, and we'll talk about them in class. Done.